Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, and we're going to be talking about if a series converges absolutely or conditionally. So let's go ahead and dive into it. This is with alternating series. So here's a great example. We have the alternating harmonic series. We know that the harmonic series diverges, but once we add that alternating piece, it converges, right? So we're going to compare it to when we take the absolute value of it. When we take the absolute value of our series, we get the harmonic series, which we know diverges. But when we have that alternating portion, we know it converges. This tells us that this series, the alternating harmonic series, converges conditionally. The alternating portion is what allows it to converge. So let's see another example of this. We have the summation k equals 1 to infinity, -1 to the k plus 1, that's the alternating portion, divided by k squared. What I'm going to do is I'm going to look at the absolute value of it. That's where we remove the alternating and we just have 1 over k squared. I know that 1 over k squared, this series, is going to converge just using the p-series test, right? P is equal to 2, greater than 1, it converges. If I were to use the alternating series test, I would also get our original series converges. That means that this convergence is not conditional on the alternating piece. If it's alternating or if it's not alternating, it's going to converge. So this means the series converges absolutely. No matter what you do, it's going to converge, right? So let's go ahead and give the definition. First, we have if the absolute value of the series converges, then we have that the series is going to converge absolutely. Doesn't matter, right? But we have if the absolute value of the series diverges, like the harmonic series, and the normal summation with the alternating aspect converges, like the alternating harmonic series, then a sub k is going to converge conditionally. So those are the two little requirements that we have here. Another way to think about it is that removing the alternating signs in a convergence series may or may not result in a convergence series, right? It might diverge or it might converge. So let's go ahead and go through some examples. If you're being asked to show if it converges conditionally or absolutely, the first thing you should check is the absolute value of it, right? So I'm going to go ahead and check the series k equals 1 to infinity of 1 over, and that's going to be k to the power of 3 halves. So using the p-series test, this is going to converge, right? So we have p is equal to 3 halves, which is greater than 1. So we know that the series is going to converge. If you check the absolute value and it converges, that tells us that our series, the normal a sub k, so in our case, that would be this series right here, is going to converge absolutely. So you're done, right? That's all the work you need to show. Let's go and see another example. So of course, we're going to go ahead and take the absolute value first. K equals 1 to infinity of, and that's going to be k over k plus 1. So if you don't immediately see a series, like it's not geometric, it's not a p-series, something like that, what you can try first is the divergence test. So we're going to take the limit as k approaches infinity of k over k plus 1. So because this is a limit at infinity, we can go ahead and just take the highest power of the numerator and the highest power of the denominator. And this is just going to be the limit as k approaches infinity of 1. Limit of a constant is just equal to the constant. And this is 1. By the divergence test, since this is not equal to 0, that tells us that our series diverges. So if it diverges, you need to go back to the original series and also test it. Because if the original series diverges, then it diverges. If it converges, then it converges conditionally. For this one, you can also use the divergence test, right? So like we said, the limit as k approaches infinity of k over k plus 1 is going to go to 1. When we add the alternating portion, this is going to diverge to 1 and -1. So it's going to be oscillating between the two. Again, since this is not equal to 0, it's oscillating between -1 and 1, then that means it's going to diverge, right? So that doesn't tell us anything interesting. We just know it diverges. Here's another series, k equals 1 to infinity of sine of k over k squared. So the first thing we're going to do is take the absolute value, k equals 1 to infinity of sine of k over k squared, right? Or if you wanted, you could rewrite it, k equals 1 to infinity of absolute value of sine of k divided by k squared, right? K squared is always going to be positive. So first we're going to go ahead and bound the absolute value of sine of k sinc. This is going to be less than or equal to 1, right? That's going to be the maximum value that it always chooses. So here, k squared, if we divide by k squared, we have that inside the summation, our little formula for it is going to be bounded above by 1 over k squared. So let's go ahead and look at the series k equals 1 to infinity of 1 over k squared. Using the p-series test, I know this is going to converge. P is equal to 2. So this converges by the p-series test. Then you can use the comparison test, right? this is bigger than this, right? We have it's bounded above like that. If this one converges, that forces our smaller one to also converge. So by the comparison test, that one is also going to converge. So since our absolute value converges, that tells us that our original series is going to converge absolutely. Here we have one more, so k equals 1 to infinity of -1 to the k plus 1 over the square root of k. K equals 1 to infinity of, that's just me 1 over square root of k. I'm going to write that as 1 over k to the 1/2 because then I can see this is a p series. We have that p is equal to 1/2, which is less than 1, so this is going to diverge, right? So since that diverges, now we need to check our original series, and I'm going to do that using the alternating series test. So our a sub k is going to be 1 over the square root of k, right? The first condition we need for the alternating series test is for our a sub k's to be non-increasing. One way you can do that is think of it as a function. So here we have 1 over the square root of x. When we find f prime of x, we're going to go ahead and use the first derivative test to find the intervals where it's increasing and decreasing. We want the intervals where it's decreasing. So this is going to be what? -1/2 x to the -3/2. That's going to be -1 over 2x square root to the power of 3. So when we set this equal to 0 and solve for critical values, there's only one critical value, right? X cannot be equal to 0, but that's okay because our series is starting at 1 going to infinity, so it doesn't include 0. So we also have the f prime of x, no matter what number we plug in for x greater than or equal to 1, it's always going to be negative, right? So this is going to be less than 0 for x values greater than or equal to 1. So since the first derivative is negative, that tells us that our function f of x is decreasing, right? For x values greater than or equal to 1, that tells us something about our a sub k, right? Our a sub k is just like a function, except it's only at the natural numbers 1, 2, 3, 4, 5. So that tells us our a sub k is going to be non-increasing or decreasing for k greater than or equal to 1. We also need to show that the limit goes to 0. So let's take the limit as k approaches infinity of 1 over the square root of k. Naturally, this is going to go to 0, right? So we have that both of these conditions are met. So because both of those are met, that tells us that our series is going to converge, but since the absolute value of it diverged using the p-series test, it's going to converge conditionally, right? So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.